Hello, welcome. In this video, I'm going to be talking to you about independence of path for path integrals of vector fields. And so I'm going to start off with an example to kind of show you how this is happening. Okay, so I'm going to be interested in integrating FDR over three different paths. Okay, but I'm going to keep them pretty simple. I'm going to let them go from the origin to 1, 1. The first path I want to consider is the straight line. Okay, and then the second path, really I could just choose any three paths I wanted, but I think I'll choose it's part of a square root curve, and then maybe kind of a polynomial type curve, and maybe I'll say that's like y equals x to the 3 over here. Okay. And I'm going to compute the integral of FDR over these three curves. I'm going to show you that they're the same. And then over the course of this video, I'm going to tell you why they're the same, what conditions can guarantee us that our integrals will be independent of path, and then I think I'll have a few more other things to say. And then I'll also work an example. Where would we use this? So I think I'm going to start with computing the integral of FDR over C1. So for C1, I'm going to need to parameterize this. I'm going to use x equals t, y equals t, t runs from 0 to 1. Okay. And so I might, I'll just, how do I want to do this? I don't know that I'm going to have quite enough room. I think what I'll do is I'll just do each of them and then erase. Okay, so f dotted with dr is what I'm interested in computing. R of t is going to be x is equal to t and y is equal to t, and t is going to be running from 0 to 1. And so what I'm going to do is I'm going to say, well, f is now f of r of t is going to be, all right, 1/2 x times y is going to be 1/2 t squared. And then 1/4 x squared is going to be 1/4 t squared. And then dr is going to be x prime of t dt, y prime of t dt, so 1 dt and 1 dt. So that this integral of f dotted with dr over C1 is going to be equal to the integral from t equals 0 to t equals 1. Okay, f dotted with dr is going to be 1/2 t squared dt plus 1/4 t squared dt. I add those together, I'm going to get 3/4 t squared dt. Okay, I'm going to anti-differentiate. I'm going to bump out the power by 1, divide by that 3 I get, and I'm going to get 1/4 t to the third as t runs from 0 to 1, which is going to be 1/4. Okay, so I'm going to kind of just write up my result here, the integral over C1 of f dr was equal to 1/4. All right, so now for C2, what I want to do, maybe organize this a little better. Now I'm interested in computing the integral of this vector field over this path. So if I'm interested in, so I'm going to parameterize first. For C2, r of t is going to be, this is like y equals square root x, but maybe, I don't know, I'll just really switch it up so it looks different for you. I'll say maybe x is t squared and y is just t. And this would be t still running from 0 to 1. So that, okay, f is now going to be given by, let's see, 1/2 x y, that's 1/2 t to the third. And 1/4 x squared is 1/4 t to the fourth. Okay, dr is going to be x prime of t dt and y prime of t dt. So this is 2t dt and just 1 dt. Okay, when we go to integrate f dotted with dr, that's going to be, all right, 1/2 times 2 is 1t to the 4th dt. So I've got t to the 4th plus another 4th of t to the 4th, so I have 5/4 t to the 4th dt. When I anti-differentiate this, I'm going to bump up the power by 1, divide by the new power. I'm going to have 1/4 of t to the 5th as t runs from 0 to 1. I think you can see where that's going. That's going to be equal to 1/4 again. Okay, so I've got the integral over c2 of f dotted with dr equaling 1/4. Okay, then for the third one, you might be saying, well, like, what if we slowed down or sped up the parameterization? Would that impact the value of the integral, right? Because I could say that x is t and y is t to the 3rd, if this is y equals x to the 3rd, which is what I had in mind. But maybe I'll kind of slow down the parameterization. I'll let x equal 1/2 of t and y be the cube of that. So that's what I'm going to do, and I'll show you that that actually doesn't really impact it at all, because any kind of, the way I mess with the parameterizations, it's kind of coming out in the dr. So for C3, I'm going to use r of t equals 1/2 t, and then I'm going to take 1/2 t and cube it, and that'll be 1/8 t to the 3rd. Because if I take 1/2 t to the 3rd power, I'm going to have 3 powers of t and 3 powers of 1/2. So then also, okay, t now is going to be needing to run from 0 to 2, right? Because I know x needs to go from 0 to 1, so t would need to be 2 to get me all the way to x equals 1. Now, okay, f, when I pass through to t, is now looking like, okay, 1/2 xy, so 1/2 times 1/2 times an 1/8 is a 32nd of x times y is going to be t to the 4th. Okay, and then 1/4 of x squared is going to be a 4th times 1/2. Wait. Oh, that's tricky. Okay, x squared is going to be 1/4 t squared, and then divide by 4 again, and I'll get 1/16 of t to the 4. Check this against. Wait, but is it going to actually be t to the 4? No, it's going to be t to the 2, right? Because it's 1/4 times this thing squared. Okay, and then dr is going to be the derivative dt, so 1/2 dt, and then 3/8 t squared dt. Now I'm ready to compute the integral of f dotted with dr over curve C3. That's going to be equal to, all right, f dotted with dr, 1/32 times 2, or 1/2 is 1/64. I just know, because I've already worked this example, I don't want 64ths, I want 128th, so I'm going to say that's 2/128. Okay, now t is running from 0 to 2. This is 2/128 t to the 4th. And then I'll have 3/128, because that is 16 times 8, t to the 4th dt. So if I add 2/128 plus 3 more, I'll have 5/128. You might be saying, oh, this doesn't look as likely to come back as 1/4, but don't worry, it will. Okay, so I'm going to take an antiderivative. It's going to be 1/128 t to the 5. Okay, so it's going to go all the way so it's 32/128, which is 1/4. And so I'm concluding that the integral over C3 of f dotted FDR is also 1/4. Now, kind of like where this is going, and I hope that, let's see, 10 minutes in, that's kind of a lot of doing path integrals and showing that they're equal. But maybe in these 10 minutes, you have noticed that this can be written as the gradient of something else. Okay? And if you didn't, it's not a big deal. That's kind of what I would have just, proposed to the crowd if I had a bunch of people in here. Hold on, I gotta go dig out my piece of white chalk that's not too short to write with. And so we can write f as this gradient field f, or the vector field f as the gradient of some other function. So I'm going to say that notice f is equal to the gradient of some other function where f is equal to, f depends on x and y and is equal to, let's see, what is it going to be? I think it's going to be 1/4 x squared y. Because if I take the derivative of that with respect to y, the y will go away, and if I take the derivative with respect to x, it'll be 2/4 x y. Yeah, I'm feeling pretty good about that. Okay, and I also want to point out that at the point 1, 1, f of 1, 1 is equal to 1/4 times 1 times 1. And at 0, 0, I've got it equaling 0. So really there's this like fundamental theorem of calculus type thing going on right here, right? Like that I'm computing the line integral, but it's coming back to be just the difference in the values of the potential functions from the endpoint. And there is something to that. That's the fundamental theorem of line integrals, is that if you have a conservative vector field and you're going to integrate that over a path, well, it doesn't matter what path you take, it only matters what the endpoints are. And I'm going to prove that for you just I think right now. So I'm going to clear that off and set up to give you the theorem. All right, so here it is. And this is the fundamental theorem of path integrals. So if our vector field is conservative, which is to say that it's the gradient of something else, and we're able to parameterize some curve, C, which has endpoints A and B, then we can compute this path integral of the vector field over some path by just looking at the difference in the potential function at the endpoints. This is really, really nice. Because we've only, at this point, studied paths that are like really convenient, right? But I think you could imagine that in general, the paths could be really unpleasant or difficult to parameterize. Or even if they were easy to parameterize, maybe something about our vector field made, actually passing it through and computing the integral really hard. But this would be great. This reduces our job to, checking to see if a vector field is conservative and then figuring out what the potential function is for it, which is not in general the easiest problem ever, but it's something that we have some experience with and we can probably do. So I'm just going to prove this theorem for you real quick. It's actually very direct. So I'm going to start by assuming that, large f is a conservative vector field. So I'm going to say, I'm just going to, remind you that large f is the gradient of this small f, which means it's the partial of f with respect to x and the partial of f with respect to y. Now I'm going to prove this for you in 2 dimensions, but the 3 dimensions it would be exactly the same, right? And so what else am I going to say here? I've got this, and I'm interested in this integral. So I'm going to say that the integral over curve C of f dotted with dr is going to be the same as integrating from a to b. Like, how do we do this? We pass it through to t. So we're going to run from a to b, and it'll be really, what we end up doing is we dot f with dr dt, and then we integrate that with respect to time. But it's, it's more compact to write it like this. But I want to actually write it like this, f dotted with dr dt dt. Okay. And let's think about, what is actually dr dt. R is going to be x of t and y of t. So dr dt, I feel like this is probably too small, but I'm going to run out of room. So dr dt is dx dt and dy dt. Right? And that means that if I take f, which is this, and I dot it with dr dt, I'm going to have the integral from a to b, and I'm going to write this on a new line because this is pretty important, and I know it's going to come together pretty fast after that. So when I do that dot product, I'm going to get fx times dx dt plus fy dy dt. Integrating that with respect to t. Then I'm going to call back on something that we probably haven't talked about for a few weeks, and that is the multivariable chain rule. Look at this. This is the derivative of f of r of t with respect to t. Okay, so I'm going to take this thing that I've kind of written here in the parentheses, and I'm going to write that as a derivative. And we know how to take the integral of a derivative, right? D dt of f of r of t. Okay. Right? If we want to take an antiderivative for this, that antiderivative is going to be f, and I'm going to plug in b and a, and I'm going to subtract. That's the fundamental theorem of calculus, so it's pretty much all over now. And this is going to be f of r of b minus f of r of a, which is what I decided to show in the first place. This is going to be really, really useful. If we've got a vector field that we can show is conservative, we've got a nasty path, we don't have to worry about the path at all, we just think about the endpoints and we make it happen. But we've got a couple more results I want to tell you about before I work an example in the video. So I'm going to, I think I'm going to clear off the first example and tell you some other stuff. So I decided to work the example now and then tell you the facts at the end. And I also realized that we hadn't really talked about anything in space, so I went and got an example of one in space. And this one's actually really nice because I'm going to integrate a vector field that we've already talked about in this video series. So a few videos back I talked about path integrals in space. I don't actually think it was that video. I think it was maybe the first vector fields video when I was talking about what made something conservative and we computed a potential function. We've computed a potential function for this one before. And so I'm going to just, kind of, without much justification, I'm going to just pull out the potential function so that we don't have to spend a whole bunch of time finding it. Hold on just a second. Let me remind myself of what video and approximately where that was in case you wanted to go back and watch. Okay, yeah, I found it. It's video 34. It's about vector fields in space, and it's at the end. And so, the conclusion that we found was that this large f is equal to the gradient of small f, where small f of x, y, and z was x squared y plus z squared y plus some constant, which was a real number. Okay? But we know that we don't, if we're going to find the difference in the gradient function, or the potential function between two values, we don't really care about this constant because it would subtract away. You're a veteran of single variable calculus, you know how that works. So all we need to do is we need to just say, okay, if I'm trying to integrate over this really nasty curve that I have no information about besides its endpoints, okay, that's a big hint. If you're given a nasty curve and you don't have any information about it other than its endpoints, well, then it's probably going to be one of these where we find a potential function. And so really what this is going to be is I'm going to start here. I didn't really imply an orientation. I'll have more to say about that in a second. But I'm going from 1, 1, 0 to x equals 0, y is equal to 2, z is equal to 3, so 0, 2, 3. And so really what I need to do is I need to evaluate my potential function at 0, 2, 3. So if x is 0, then it'll just be z squared y, so 9 times 2 is 18. And then f of 1, 1, 0, this is where z is 0, so that second term is going to be 0, x squared y, that's going to be 1. I will conclude that this is equal to f of 0, 2, 3 minus f of 1, 1, 0, which is looking like 18 minus 1 to me, so that's going to be 17. That was much easier than getting a parametrization for the curve, running it through the whole integral and everything, all that good stuff. We just need to find a potential function, subtract it, just like the fundamental theorem of calculus. Okay, so this is an example of how we will use this. I need to tell you a couple of other things, but I'm already over 20 minutes, so I'm going to really try to give this to you as directly as possible. Okay, so one thing that I don't think should be too surprising if I pointed it out to you like this, and I know that there has been some discussion of this in physics, is integrating a conservative vector field over a closed curve. So we'll kind of use that to indicate that this curve is going to be closed. I saw that in one of the textbooks they'd even put a little arrow to indicate that it had a clockwise orientation. Sometimes we'll be more concerned with the direction of the orientation, I think, in the next video when we talk about Green's theorem, which will be another nice way to compute these things. And what was I thinking? Oh, that path integral over a closed curve of f dotted with dr, that's going to come back 0 if f is conservative. Okay, and this is going to be really quick for me to show you why, right? Because if f is conservative, then we have independence of path, and we can also use the potential function thing, right? So I'm going to say, okay, so let's say, suppose C is a closed curve, and let's maybe dig down a little deeper and see what does that actually mean. So suppose C is closed. Okay, that means that, okay, we're going to parameterize C with R of t, some vector value function. And, well, we're going to start at A. And we're going to let this thing do whatever it's going to do, but the fact that it's closed means that the ending point is the same as the beginning point. And so A to B is going to be kind of the t values that I'm going to, parameterize this curve C with. Okay. Well, I already know it. If f is conservative, then we will have f equals the gradient of some other potential function. Okay, which means also that the integral over curve C of f dotted with dr is going to be, what was I going to say? The bell, it distracted me. It's going to be f of r of b minus f of r of a. And since r of a is equal to r of b, f of r of b is equal to f of r of a, which is going to have to equal 0. Okay, and I think there's some pretty important physical interpretations of that. I need to also, because a lot of the vector fields that you study in physics are going to be conservative in any of the force fields like gravity, electric field, magnetic field, I believe they're going to be conservative. So that's going to be useful. Okay, I was planning on telling you that if for some reason you can find out that your path integral of a vector field is actually independent of path, that is evidence that you have a conservative vector field. That was the definition of conservative that some other textbook or something on the internet had taken, which I found kind of interesting. And then they showed that, that guaranteed the existence of a potential function somehow. And so I was going to show it to you, but there's this one step in the proof that I'm really not sure. Everyone just keeps saying, oh, hey, this integral doesn't depend on x. But they don't tell me why. I looked in 2 textbooks and 3 sites on the internet, and it wasn't really explaining to me that. So I'm not going to go through and show you that. But I will tell you that fundamental theorem of line integrals, it actually or the independence of path thing, it actually goes both ways. Okay, so just remember that if the vector field is conservative, then we can just use this trick where we're going to use the potential function to evaluate a path integral rather than going through the whole rigmarole. And that's all I got for you today.